Hello, my name is Chenqin Li, and today I'm going to go through a question which is an application of Gauss Divergence theorem that can be used to solve the net outward flux through a surface. Looking at the concept, if the region is closed, then we can rewrite the double integral over the surface into a triple integral of the divergence of the vector field. The question asks us to find flux of this given vector field above xy plane, bounded by the given cone shape and also the plane z equals to 2. To start the question, let's have a look of the graph, which clearly shows there are actually two parts of the surface. That is, S1 is the disk at the top when z equals to 2, and the surface around the cone. Therefore, to find total flux across the surface, it needs to be the sum of two double integral over S1 and S2. It may take quite a lot of time to compute the calculation, as the shape is a closed region. We can actually apply Gauss Divergence theorem, which simplifies the calculation a lot. To compute this triple integral, firstly, we have to define the volume. And as we are talking about the entire cone, so it gives us theta is from 0 to 2 pi, and it has also been given in the question that z is from 0 to 2. And then we can parameterize the shape by using the polar coordinates. It is relevant to a disk. By taking x equals to r cosine theta and y equals to r sine theta into a given cone equation, z squared equals to x squared plus y squared, we would have this equation, and we can take the r squared as a common factor to the front, which would only leave us cosine squared theta plus sine squared theta in the bracket. And we know this part is always 1, so we would have the conclusion that is z squared equals to r squared. Because in this question, we are only considering the situation that z is above the xy plane, so z has to be positive. So we can conclude that r equals to z. Here I draw a lateral view of this cone shape. When r equals to 0, that is the center of the cone. And this linear equation, r equals to z, this actually describes how far can we go for the radius from the center to the side of the cone. So as r actually depends on z, we really need to be careful with the order of the integration. We need to integrate r before z. So far we have already get the region of this volume. And then the next thing we need to compute is the divergence of the vector field. So given f equals to xi plus 6yj plus 3zk. To find divergence of this vector field, we need to find the partial derivative with respect to x, y, and z of each part of the given vector field. This would give us 1 plus 6 plus 3 is equals to 10. Bringing this to the triple integral, and don't forget Jacobian part. As this integration, we can bring the 10 as a constant to the front. And by following the steps, this would give us the z squared over 2. So we can also bring the 2 on the denominator to the front, so 10 divided by 2 is just 5. Notice here that the only variable we have is z here. So instead of this double integral, we can actually split that into the products of two integration. And this part will just give us 2 pi, and this part we can calculate it as 8 over 3. So 10 pi times 8 over 3, this is going to be 80 over 3 pi. And that's the end of our question.